Yeah, if you've ever talked to anybody who's done very much wide area distributed management, one of the things that they really want to do is monitor the systems that are out there, make sure that everything's up, understand what's going on, and be able to tell that they are in compliance, right? So FrogNet is no different, but the way that we go about it absolutely is because in traditional systems like the ones that I worked at when I was with Microsoft, uh, the the method for doing that involves a great deal of rest, a lot of distributed systems, uh, databases, both on the client machine and on the server machine, coordination like crazy. You've got policy, all kinds of things that can go wrong, and you've got to get them all coming together at the right time in the right place. And it's a very delicate dance, and it's very easy to break it. So when I started doing FrogNet and started working with the FrogNet memory, which gives me memory that is network addressable without having to have any of those messages in place. Uh, the FrogNet monitor was one of the very first things that I built, and the FrogNet monitor is a system. There are four machines up on the screen right now. The one on the top left is Seattle 5. The one on the top right is a machine called Happy Dog. In past videos, that has been New York 1, but in the installation video, we renamed it to Happy Dog, so it's Happy Dog now. Down on the lower left is Seattle 6, and on the lower right is Seattle 2. And you can see each one of them knows about all the other machines in the network. And for any one of those machines, we can, so we're on Seattle 2 now. We're going to go to, say, BA MacBook and load up the sensors for it. So we just hit return and that loads up the sensors. Now, these are the sensors that we know about for BA MacBook. And we can do the same thing up here, like for Seattle 2. And we can say Seattle 2, for example, has a GPS sensor in it. So that might be more interesting. And that's just the GPS data for Seattle 2, right? Uh, the system perf information is what we're mainly interested in here. The system perf information gives us information about the CPU, the disk, the memory, things like that that are on the system. And you see all this is coming back in the form of a JSON bag, right? So this is all FrogNet memory. A producer is writing these JSON bags out to FrogNet memory, and it's writing them in terms of the tuple is it is a this is a sensor type, uh, the sensor name, and the sensor address, and then the data is the JSON bag that goes with it. So the sensor type here, system perf, that sensor type, for example, I can go to the FrogNet monitor here, or I can come down here and look at Seattle 2's system perf. Actually, let's use this one. Seattle 2's system perf, and we'll see that it's got the same frog ID, right? So this is the same data, and I can get to it from wherever I need to on the network. So I can go down here. These on the bottom are, this is Seattle 2 and Seattle 6, yeah. So here it's got the same frog ID. So these are all reading from the same tuple space, the same memory, right? And it's across the board, and I don't have to be exchanging messages to do that. All I do is say, give me this piece of sensor information, or give me all sensors for Seattle 2, or give me all GPS sensors, or whatever I want. The way that we get to the actual data is of our own design. So with the FrogNet monitor, this is the first time we really implemented FrogNet memory the way that I want to see it, the way that I want to think about it, which is that we have producers and consumers that are working on independent memory. or they're working on memory independently, I guess is what you would say. One is producing data in its own time, the other is consuming data in its own time. And the FrogNet memory, yes, it's a database, but there's only one record. It is the current record, and the FrogNet memory floats as we move around. If this one says Seattle 5 is the database host, if I were to reboot Seattle 5 for the time that it was down, it would flip over to one of the other machines for the database host. It is always there, it is always available, and if it's not, it switches to the next one. So you will never be unable to get to the network memory, although the network memory may be narrowed to your own individual network. But even then, all the 254 addresses on your network can share that same memory in exactly the same way. So it's not that this has to be network to network. It can have value on your own local network, but when you go network to network and you can say, I need to monitor the sensors that are in London and Istanbul and Paris at the same time and make a decision on them. That's where we really shine with this thing. And the whole thing, by the way, is still done with FrogNet semantic compression. And so I can do what we're going to do here. This is one of my favorite tests, right? Is the pipe test. I know you've seen it before, but I'm just going to run again. So we're going to do a pipe workload, and we're going to go to Happy Dog. So FrogNet host.happydog, and we're going to do an echo test, which is the same diff test. We're going to do 300 of them. And what it's doing here is this one should come back very fast with very high simultaneous counts. We got 5.1 on standard Apache. We went up to 9.3 when we just switched to semantic compression. We in the ramp we got up to 80, which is good. In the burst we got up to 38.4. Now that's going one direction. If we go the other direction, we'll probably see different numbers. So if I do a pipe workload to FrogNet host dot Seattle 5, and we're going to do the echo test again, and we're going to do 300 of them again. So this time it's going the opposite direction. The first time it went this way. This time it's going this way. 5.2 again for the baseline. Then when we switch to semantic compression, it only went up to 5.3, so it's warming up a little bit. We got 80.5. That's the same as we got before. And then on the wire, though, we got 119.7. So that's a huge difference. This one would probably do the same if we did it the same way. Now, the big interesting one that we're going to run here is the megabyte test, and we're just going to do 100 of them. But what this is doing is sending a payload that has 6 dynamic fields in it, but the payload is a megabyte in size, both directions, and it sends them through and figures out what the frame rate, what the rate is, and how much data you're actually sending, and that's the really interesting part on this. So the baseline we got was 1.2 requests per second. When we switch over just to using FrogNet, we get 3.2 requests per second. But this is the important part. Look at the bytes sent. We only sent 3.4 kilobytes instead of 31 megabytes. Now we would have sent 31 megabytes without the engine. So we saved, 31 megabytes because we only sent 3.4. The same thing here in the ramps. We sent 13.5 kilobytes instead of 113 megabytes. And then down here in the concurrent workload, we got 8.6 requests per second. We sent 14.7 kilobytes. We saved 124 megabytes, right? So that's what semantic compression can do for you. That's what FrogNet memory can do for you, and that's what the whole thing is designed to optimize for. The ultimate expression of FrogNet memory is, of course, through the communicator, and I encourage you to watch that. But for now, this is the best way to do it. There are additional bindings for FrogNet memory in C Sharp and C++. You can find those in user local bin. So it's user local bin, and here there's FrogNet under monitor under, and you'll see there's CPP, CS, PY, and then there's a shared directory for it too. There is also, and this is kind of cool, I should have shown you this earlier, this is the network's living topology. So this is what the network looks like right now. And this is also driven by FrogNet memory. So all of these values are being read directly out of the database as we're moving along. So here's Happy Dog, and here is somewhere down here. There's Here it is, system perf. I apologize for it didn't occur to me that this was going to be such uh, bad imaging. Uh, so we'll just skip this, but basically you can see you've got JSON here. So it is doing the JSON the same way as it's doing before. We're going to close off this, but this is what you've got. So here's your internet egress. Here's New York. Here's the other New York. Here's the third New York, and here's the fourth New York. And then these three are the Seattle machines, Seattle 2, 5, and 6. And these lines represent the logical connections between the machines. So this is a routing and topology map. And this is generated live. I mean, how many times have you wanted to see something like this and had to generate it from God only knows what? But now this is just live because it's being read from the topological database the way that it should be. All right. So that's the monitor. Like I said, what we want to see is the communicator. We'll get to that, but this I hope gave you a decent introduction to what FrogNet memory is and how to access it. Bye.